Welcome to the midterm demo for Group 19. We will be demonstrating our current project progress and showing some of the functionality we have achieved thus far.
Hi, my name is Danny Rodriguez, and I'm an electrical engineering major.
Hello, my name is Midterm, and I'm a computer engineer.
My name is Noah Rooks, and I'm an electrical engineer.
And my name is Esperando Elbon II, computer engineer. Here's a quick overview of the parts of our system.
This is our main PCB. It's 156 by 206 millimeters. Planning on downsizing that to make it better fit into the constraints of our Century. Our USB ESP32 right here. We have our 3.3 and 5 volt regulators, LEDs indicating that they are in fact working, which they are. Our USB plug-in, USB to UART. The assortment of plugins for our different ultrasonic sensors, camera, BME multi-sensor, and camera plugin. As you can see here, these two are our single H-bridge motor drivers. These right here would be our motor driver that I developed, which still needs to be modified since it is not working, and this is the BME module that I designed that also needs to be modified as it is not working.
So this is our mic and BME. It currently functions as we wanted it to. And our 12 volt battery on the bottom of our Century, Talon Cell 12 volt, it currently works and it's accurate and we tested it. Everything's functional to the way that we wanted it.
Let's take a look at system functionality. Imagine you're getting ready for work and you're running late to drop your kids off for school. As you go out the door, you don't remember if you turned off the stove. You reason that it'll be okay and you don't think anything further of it because of how late you are. Unfortunately, it turned out you did leave your stove on, and by the time you drop your children off to school and are on your way to work, your house is currently catching on fire, and when you get back home later that day, you'll have to file a claim with the insurance company. Now imagine a better scenario where you had activated the seams before you left. You would have had one of two options. You could have taken a quick second to take manual control over the Century and drive it to your kitchen to actively inspect the stove yourself and see if you left it on. Alternatively, you could wait until the Century sends you a push notification indicating that overall temperature in your home has increased past a certain level that was custom set by you. This scenario highlights the main functionality of the seams, which is to help you know what's going on when you're not around in order to foster within you complete assurance under constant watch. A key part of getting seams to function correctly is being able to connect to and maintain a Wi-Fi connection in order to communicate through Firebase with CenturyLink. Here's a demonstration of that functionality.
So here we're going to demonstrate the functionality of our Century connecting to Wi-Fi via Bluetooth. As you can see in the database, there is nothing, and that reflects on CenturyLink. Equally, there is nothing. So using the Terminal app, we'll connect to the Century's Bluetooth server. And then we're going to go ahead and send over our SSID for our Wi-Fi network. After sending that over, we should receive a success code. We receive success code 4, indicating successful transmission. Sending over our password. Again, received success code 4, indicating successful transmission. Now we need to disconnect and wait for it to connect to Wi-Fi. And as you can see, it's connected to Wi-Fi. Readings are reflected in both the database and the partner app.
Let's take a look at our key engineering specifications and the progress we have made implementing them thus far. Our microphone should be able to measure anywhere between 35 and 120 decibels. Our camera should run at a frame rate between 30 and 60 frames per second, and our temperature sensor should be able to measure anywhere between -55 and 150 degrees Celsius.
Next, we have our all-in-one environmental sensor, the BME 688, which measures temperature, humidity, and pressure. Here we are showcasing real-time data captured from our sensor, and this is plugged into our main PCB. According to our engineering specifications, we require a pressure range of approximately 300 to 1100 hectopascals. Additionally, the Century must be equipped with a sensor capable of accurately and consistently measuring temperature across a specified range of -55 to 150 degrees Celsius. However, Given our current indoor setting, we are unable to demonstrate significant temperature or humidity changes in real time. To observe such variations, we would need to place the sensor in a controlled warm or cold environment. Similarly, the atmospheric pressure remains stable in this setting, preventing us from showcasing dynamic changes. That said, we have confirmed that the sensor meets our required specifications. In the future, we will conduct future testing, including specific scientific comparisons and controlled experiments to validate its accuracy and performance against a baseline reference. I'll be discussing our preliminary temperature accuracy testing for our sensor system. Our goal was to verify that the temperature readings from our sensor were accurate when compared to a known true source, an analog thermometer. As you can see in the image, we placed a traditional thermometer next to our system, which includes a digital sensor connected to a display. This setup allowed us to periodically check the sensor's temperature readings against the thermometer's values. Our initial results showed that the sensor's readings were consistently within 1 degree of the thermometer's measurement. While we didn't formally collect data yet, the consistency of the readings suggests that the sensor is reliable for general temperature monitoring. To further improve accuracy testing, we plan to conduct more controlled experiments where we record data at different temperatures and analyze potential variations. This will help us determine any sensor bias and ensure long-term reliability. So far, our sensor is performing well because additional testing will provide more clarity. This is just the beginning of our validation process, and we'll continue refining our approach to ensure accurate environmental monitoring.
We measured sound in different environments at different sound levels. The accuracy of the readings is questionable and might have to do with the MCU's ADC, as there are known nonlinearity issues, which might require some further calibration. And the following is some of the measurement process. We're demonstrating the DR robot electric microphone for our 8th engineering specification, being the ability to read in a range of 35 to about 120 decibels. We are unexpectedly experiencing low decibel readings while it's plugged in the main PCB, so we are currently having it plugged into a separate ESP module for this current demonstration. We'll hopefully get that fixed in the next week or two. As seen in this first application emulator, the current readings are falling to about 60 dB throughout these varying ones, which is alright for just a standard reading in an average room. This next demonstration will be for a quiet room. Pretty quiet, yeah? Alright, this next demonstration will be for our loudness test. Action.
For our camera measurements with regards to frame per second, we have methods for our future testing that we'll be implementing. One of them will be adding a quantification FPS counter where you'll be able to see the exact number of frames on the screen, and we'll also use the hardware to output timestamps each time a frame is captured. So one of our requirements that we'll be adding on our Seams robot is that the sensor should output the video it captures at a sufficient rate to ensure the undamaged video playback on a compatible device. This means we need to display it on a high frame rate that's around 30 to 60 FPS to ensure that the users using the CenturyLink app will be able to see and monitor the environment around them. Now over here we have our ASP32 cam with an OV5640 lens, and we have our partner application here, and as we can see, when we hit the start record stream, it doesn't connect directly because the ESP cam is not connected to the internet or to electricity. So now once we connect the ESP32 cam, and we hit the start the stream, we should be able to see that the camera displays the area around it with a sufficient resolution and a high frame rate so the user can distinguish the objects around it. This is a test to test a camera through a hallway. Now we will be demonstrating the results through the partner application app. This is a test to demonstrate the distance that the camera can cover.
The ultrasonic sensors are an important part of the system that serve as its present sensors and obstacle detectors. We measured at many distances and took the average of 3 readings per distance measured. The percent difference between the readings and actual distances were always less than 5%, showing good accuracy on our sensors. Following is some of the measurement process. Here's a test showing the ultrasonic sensors measuring the distance of 5 inches. Here's a test showing the ultrasonic sensor measuring the distance at 20 inches. Here's a test showing the ultrasonic sensor measuring a distance of 30 inches. And that concludes our presentation. Thank you for watching.